All right, so our idea of potential energy. And maybe I shouldn't even say a better PE formula. Maybe it's just a different potential energy formula, but I'm going to call it a better one right now. The problem with our potential energy formula is that if PE is equal to mgh and you move away from the if you move away from the surface of the earth and you get higher and higher up in the air, right, or an object is higher and higher up in the air, your PE just continues to get larger and larger indefinitely, right? It gets to a point where I guess if you were infinitely far away from the earth, you would have an infinite amount of energy, right? So you would have all the energy in the universe just by moving away from our planet. So this this really doesn't make sense. In fact, the opposite should be true, right? If you move infinitely far from our planet, then you should have no potential energy. You should have zero potential energy. So let me write this down. At infinity, right? Or a distance of infinity, your PE, gravitational, right? UG, should equal zero. Right? You should have no potential energy when you're infinitely far away. So we have to fix this formula. This formula that we've been using just can't handle it, right? So let's take another trip down memory lane back to last year when we learned about setting our force gravity formulas equal to each other. The reason we did this is because we like to say that mg, our weight formula, is equal to the universal gravitational formula. Over r squared. And this was, say, the mass of you or the mass of an object in a planet's in the Earth's gravitational field, right? And so because of this, we were able to say the mass of you doesn't matter. You don't affect the Earth's gravitational field. It's just going to do what it wants, and it's going to be equal to baby g, where this is the mass of the Earth divided by the distance from you to the center of the Earth. And this is equal to 9.81. And you can plug the mass of the Earth in here and the distance from you to the center of the Earth and 6.67 times 10 to the negative 11th if you so choose and you want to. But this was our formula for the G, not just the G value of Earth, right? But the G of any planet, the baby G of any planet. And so that's a decent formula to know for the AP test. All right, so what we're going to do is we're going to take our UG formula and you can kind of see, you can probably already guess what we're going to do, right? We're going to take this and put it right there for baby G. And if we do this, and this is the mass of the object, right, or the person. I'm going to say the object times big G m planet over r. This should be r squared. Dang, how did I lose that r squared? It's getting late. All right. And what you should notice here is that h is going to be to make it universal, right, we're going to make it R, right? Instead of having this zero level at the ground, which is this arbitrary, idea of, oh, there's zero potential energy at the ground. Okay, well, why? We just arbitrarily decided that. So instead of having that, we're going to have, instead of H, we'll have R. So we're going to make that substitution that for H, right? For H, we're now going to replace it with R, right? And we replaced baby G with that. All right, so long story short, we get a new formula, and this is the one that's on the formula sheet for the AP test for UG, for potential energy gravity, a more universal one, right? Where we have the mass of the object. Actually, let me write it the way they write it on the, I'll write it both ways. I'll stick with the way I'm writing it right now, and then I'll turn around and write it the other way. Times the mass of the planet over, look at this, there's a little bit of canceling going on, over just R. So it looks very similar to the universal law of gravity, gravitational. Oops. And but with one less R on the bottom, right? And this, like I said, is on the AP formula sheet. I think they write it instead like this. Right? They use capital M for the planet, little m for the object, and R for the distance, center to center. And that's important to realize, that R equals the distance center to center. So it's not really the radius, right? Sometimes it's the radius, but it's the distance center to center between the two objects. And that's important to realize. All right. Good. But does this solve everything, right? Well, no. Here's why. When we go higher up in the air, an object is higher up in the air, potential energy increases, right? We saw that with our previous formula, that the greater your height, the greater your potential energy. But we have this problem. Let me write this down, because this is what we're trying to square away here. So the greater an object's height, say on the planet Earth, the greater its potential energy. But we want UG, so these are kind of like our problems we have right here. UG should equal 0 at infinity. So how can we have this both ways, right? How can potential energy increase with greater heights, but still have UG equals 0 at infinity? If we look at our new formula here, we see that as R increases, what's going to happen to potential energy? Well, as the bottom of this fraction increases, we know that we know that the potential energy gravitational will decrease. So that's good, right? That solves, well, I don't know if I should say that's good. That helps solve one of our problems, right? That as we get to infinity, that UG should be 0, right? This is obviously going to be like a limit, right? As R increases to infinity, as R approaches infinity, UG approaches 0. So that's like a limit, right? Um, but I don't think we can say that we've satisfied the top part, right? That the greater an object's height, the greater its potential energy. That would actually be the opposite. So we didn't solve this first dilemma, right? That's got to be true too. So what do we do, right? How do we make this a formula that can accomplish these goals? And so what the trick is that we do, and I don't think this is on the formula sheet on the AP test. I don't think they've added this part. Is it might be. I gotta look at it again. Is we make UG, potential energy, negative. All right. So our formula becomes this. All right. Now, all right, this is interesting, right? And we should be able to say some things about this. Something I do want to delve into that and go into that. I was going to mention limits, and I think I will come back to the limits part of it. Let's go ahead and talk about why this is, or what this is saying, and what's true about this. So what we're saying then, and maybe I can, let me see if I can maybe draw an example. This is kind of similar to the example I was going to do. If you have an object that is right here on the ground, it has potential energy, right? Because you might say, well, I thought the ground was 0. Not anymore, right? Now we're using this distance r. So it has potential energy that is negative according to this new formula. And so maybe it has a PE here of, I'm just going to make something up. I'll say UG equals negative 1,000. If you do work on the object and lift it up to say here, you put energy into the system, into the object by doing work, right? So now it has a UG of say negative 500, right? Because you did work on it. So what I'm saying here is that this is a larger amount of PE. So, or UG. Let me get rid of that little tail there. It looks like a negative sign. It's not supposed to be there. I just miswrote. This is a larger amount of UG. So I'm saying a smaller negative number is a larger amount of UG. So we've added energy in to make the number, not its magnitude larger, but the amount of it larger by making it a smaller negative number. and so what I'm saying here is that if we continue to add energy, potential energy in, right, we're eventually, if this object gets far enough away, say maybe this is I'll call this R1 and this R2. Obviously R2 is larger, and maybe this is R3 and this is infinity, then obviously UG would hit 0. So this solves our dilemma, right? Now, by making potential energy negative, we can see that we approach, as r gets larger, we approach, or as r approaches infinity, UG approaches 0. And furthermore, we're able to add potential energy into the system, right? Increase the amount of PE, because a smaller negative number is a larger amount of UG, of potential energy. So what I'm saying is this negative 1,000 has less potential energy because it is a larger negative number. So I'm saying a larger negative number has less UG. All right. Okay, so what about the opposite? What if you kept getting closer and closer? You brought this object closer and closer to the center of the Earth. So what if it got to, say, right there, right? Well, then think about that for a second, right? I'll call this R naught or something. Then UG would be an even larger negative number, maybe negative 1 million, right? So it'd have even less potential energy, right? And so what we're saying is that the closer it gets to the center, that it's going to approach what, right? As R gets smaller and smaller, as R, right? R is right here. This is now very small. As R approaches 0, what does UG approach? Well, UG would approach negative infinity, right? So, so what I'm trying to say with limits here is kind of like this. Let me write this down. Call this a look at limits. See how good my limit analogies here work, or we'll see. So as R approaches infinity, right, in the first case, so I have something like this. UG as a potential energy as a function of R, right, equals 0, right? So UG approaches 0. So as R, let me say this again, as R approaches infinity, the function UG as a function of R, right, approaches 0. Or I could write it, the limit, okay. I could write it this way, I think. The limit as R approaches infinity of the formula, right? Negative G M1, or I'm gonna use the other way I wrote it. Capital M, little m, over R. That approaches, right? Which is UG as a function of R. That is what it looks like. Approaches 0, right? Okay. Or we can also say, right, the limit as R approaches 0. So this was the second case, right? As we get closer and closer to both objects occupying the same place in space, right? That can't happen, right? So so what I'm saying is this box, or whatever this is we were lifting up, cannot occupy the same space as the Earth. So this makes sense that we never reach this limit, right? The same with infinity, right? Traveling to infinity, you can't do that, right? Anyways, let's write this out. So I'm saying that the function UG as a function of R, right, is equal to negative infinity. So I'm saying that as R approaches 0, the function for potential energy approaches negative infinity. Or, yeah, that's what I'm saying. UG approaches negative infinity. Another way I could write it is the limit of r approaches 0 of negative g m little m over r is equal to negative infinity. So in one case, I just wrote the function out. In the other case, I wrote potential energy as a function of r. Okay, so I think my my interpretation of that to math is okay, but I think maybe my writing the limits is a little sketchy, but you get the idea. All right, let's keep experimenting with this, and I think it'll make some sense. Or actually, let's go back. Let's go back for a second, and before we do an example, I actually have an example I want to work out. But let's go back and look at the elliptical example from earlier. I think this will be good for us. So let's go back to look at Kepler's second law. And back in Kepler's second law, we had something like this, right? And we had our sun right here, and one of the focuses, and we had our planet. Where am I going to draw this? Just draw it out here, I guess. And what we said is that the planet right here, going from, say, here to here, swept out an equal area as the planet when it was right here to, say, here. Because that was what Kepler's law stated, right? That those two areas have to be equal. This area and this area have to be the same. And maybe I could have even went a little further. I always feel like I don't go far enough with that. Dang, erase my whole problem. Let me go a little further. Maybe something like that. Sure, my drawing's not perfect, but try and make it a little bit better so that these two areas are the same. So we said that the planet goes faster here and slower here. So what I'm saying here then, you can kind of think of it like the planet is falling back towards the sun, right? So here, the PE is a large negative number, right? The PE is small. And it is and by small I mean a large negative. Let me not write the word out. Just use a negative sign. A large negative number. Okay. And the KE is large. And I think this is actually going to be a large positive number. Now, they're not going to balance out to 0. They're actually going to balance out to a negative number. The total negative energy, or the total energy, let's write this down here. E total, which equals KE plus UG, believe it or not, is going to be a negative number. And that's because this is a bound system. I'll elaborate on that in a little bit here. All right, so out here, we know that UG is going to be large because it's further away, but that means that it's going to be a small negative number, right? And KE, because it's moving slow, is a small positive number. And E total is constant, meaning it's going to be this constant negative number. All right, so the reason the negative energy is constant is because there's no other forces between the star and the sun and the planet to do work, right? So the energy has to be constant here. Why is there no work being done by forced gravity? Because we have potential energy gravity. So there's no external force to do work on the system. So we end up with a bound system with a total negative energy. All right. I do want to talk about, and I know this isn't, I think this is interesting why it's a total negative energy. This actually does show up on a multiple choice on the AP test, that the total energy of a planetary system is a negative amount for a bound system. But they never explain really why. And it's kind of interesting, actually, why. But once again, we kind of got to take a trip back to what we talked about last year with circular motion. So we'll do one last derivation here, and we'll talk about a bound system here. So, and this should wrap up this lecture. So we'll call it, I don't know, I'll write, I'll just get it started here. I don't need to give it a title or a subtitle. If you remember from last year, we said Fg equals Fc, right? But we had a way to solve for the velocity for the velocity for a satellite to have a stable orbit, right? And what we said then is we set the universal gravitational force gravity, right? So we said G. Should I use big M, little m here? Doesn't really matter. I guess I'll use M planet, M satellite. All right, and we used instead of calling it a satellite, let's go star. Let's stick with what we've been doing, right? Which was M sun, M planet, right? Because that's what we're trying to explain. Let's go ahead and just stick with that. So we'll say over r squared, and over here we have mass times centripetal acceleration, which is v squared over r. So last time we solved this for v, right? So this time we're going to do it a little bit different. Object in circular motion is the planet, so I'll go ahead and identify that mass. I'm going to go ahead and start doing a little bit of canceling here. So we'll go ahead and get rid of mass planet on both sides, get rid of one of these r's, and then go ahead and write the fact that v squared then is equal to g, the mass of the sun, over r, right? And so we could find the velocity for a stable orbit for a planet, right? Or if this was a satellite orbiting a planet, then we would have the velocity of the satellite, and then instead of mass of the sun, it would say mass of the planet, right? So we could always take this a step further like we did last year and write this as VSAT equals square root G M planet over R, right? If we want to talk about the velocity to maintain a stable orbit for a satellite. Okay, but here we used the sun, and so obviously this is the velocity of the planet over here to orbit the sun in a stable orbit. All right, well, let's actually work with this formula, and we're going to come back to it here in a second. But let's think about this. Let's think about what is the kinetic energy of that planet, right? And if we think about that, we would be like, well, the kinetic energy of the planet is equal to 1/2 the mass of the planet times its velocity, right? V planet squared. Okay. Well, all right. Then if that's the case, then we can solve for the kinetic energy of the planet, right? Which is 1/2 the mass of the planet times, well, V planet squared. We can just sub in this right there, right? Okay, cool. So we're going to go ahead and say G M sun over R. Okay. Well, let's go ahead and keep this half out. Let's go ahead and push that mass of the planet in to the parentheses. And this should look really familiar right here, right? That's our new formula for potential energy. So what I'm saying here then, right, is that, well, it's not quite that, right? It's close to it, right? Because we know what the new formula for potential energy really is, right? It is with the negative sign. So there's no negative sign there. So let's talk about that, right? We have UG equals negative G M sun M planet over R. So what I'm saying is then, if we solve this for G M sun M planet over R, we see that we kick the negative sign to the other side, right? We can say then that negative UG, right? Because UG itself is negative, but this isn't negative. So if UG itself is negative, what is this right here in terms of UG? So if that makes sense, hopefully that does. So what I'm saying then is, let's write an expression for G M sun M planet over R, which is what we have, in terms of UG. So we're seeing that negative UG, right? Because UG is negative, but the negative of the negative is a positive. So in what we have here is a positive. So we're saying the negative of our negative UG, right, is that in yellow. So what I'm saying then is this right here is equal to negative UG, the positive G M sun M planet over R. Because of that, we're going to sub in negative UG right there. So what we proved then is that the KE is equal to 1/2 negative UG. So KE, let me rewrite it one more time, is equal to negative 1/2 UG. All right. So now we have an expression for the kinetic energy in terms of UG. Okay. So what we can say then is that, let's go ahead and write this out. We can go ahead and say E mechanical energy, right? Or we can call it E total, is equal to KE plus UG, right? That's what we've always said up until today, right? So let's go ahead then and sub in what we just learned. So this guy right here, let's sub that in right there. And if we do that, we see right? Okay. And you might say, well, I thought E total was negative. It was a negative number. That's what we went in saying. And it is, right? Because UG is negative, right? This is a negative number, right? It is negative G M sun M planet over R. And so the total energy is half of the potential energy, and it is also a negative number. So this proves that the total energy is a negative amount. All right. I'm sorry if that was confusing. If it makes sense, then awesome. And so what our conclusions are then are this, and I guess we can write some of these down. The negative total energy is a characteristic of a bound system. What is a bound system? It's a system where the satellite I think has just one T, where the satellite is bound to the central mass by the gravitational force and cannot get away. All right, I want to show you a couple diagrams, and then we'll end this lecture. All right, so to end this lecture, I just wanted to look at some graphs that I thought were pretty neat. And this first one, this is a gravitational potential energy curve. Like we were talking about how gravitational potential energy is negative, and then we can see that it approaches, as R approaches infinity, that potential energy approaches zero, right? So that's cool right there, we can see. So that was that limit we were talking about. And then go in the other direction, that as potential energy approaches negative infinity, because as the two, like the object and the Earth get closer and closer together, where R approaches zero, we see this happening too. So this is what the graph would look like, but then it goes on to say that it's not physically possible because obviously two objects can't be in the same place. All right, so that's cool. And once again, if you look at the axis, you have potential energy on the y-axis and R on the x-axis. This next curve is not quite maybe, or it's kind of like what we were talking about, right? But I'm trying to make sense of it completely. What it says here, though, and I think what you have happening is that at this initial point, this before point, you have an object that is going to fall towards the Earth, right? And so at this point, it has potential energy, but notice that it has no kinetic energy. They say here that the kinetic energy is the distance from the PE curve to the total energy line. So this gap here, right, is your kinetic energy. But there's no kinetic energy right here. So what I'm thinking here is this is an object that's not moving right here and then is dropped towards the Earth. The part that I'm a little confused on is what happens beyond here, where the potential energy goes on to become a smaller negative, approaching zero, like we said. But then, obviously, something would have to be done here to keep the total energy negative. So maybe kinetic energy would have to, or negative work would have to be done. I'm trying to grasp how that's the case, but I'm not too worried about that one. The graph I like better actually is coming up here, and I'll show you in a second. This one just gets at the minimum velocity formula that we talked about last year, right, to maintain a stable orbit, which was that v, or it's not even minimum, it's just the velocity, right, to maintain a stable orbit. I guess if you go faster than that, you're going to start to become in an elliptical orbit, and if you go slower than that, you're going to start to come out of orbit. So there's an ideal velocity there to maintain a circular orbit. Okay, for a satellite. This one kind of shows Kepler's second law, but it says angular momentum is conserved. And we didn't talk about this, but this is going to show up on the AP test. So why is this? Well, if we think about it, angular momentum, we said that if we think back to angular impulse, right? We didn't have a variable for angular impulse. We just called it delta L, right? We said last time that impulse is equal to force times time, right? And an impulse was delta P. So angular impulse didn't have this J variable. It just got delta L because angular momentum is L, right? So, and P is regular momentum. But anyways, instead of a force here, we have a torque, and then we have a time. So we like to expand this out into LF minus LI equals torque times time. But we said that when there's no torque, which would be the case here because the angular momentum is generated about an axis right here, right, at the sun. So here is your R. And if you have a force, gravity, this R that points along R towards the pivot, right? This is the pivot right here, this point right here, then you're not going to generate any torque. And so what I'm saying here is torque is going to be equal to 0. And because of that, for a planet and a star or two objects in this that are in a bound system like this, right, there is going to be no external torque. So we see LF minus LI is equal to 0, or LF equals LI. So angular momentum is conserved. All right, so that's kind of neat there to see. And we also said energy is conserved earlier in the lecture because there's no external force to cause work, right? There's just the force gravity, and that is already taken care of in the energy formula as potential energy. I guess if you made the system just the planet itself, then force gravity would do work. But that actually does show up in a problem as well. So I'll have to point that out when it does. This is the graph that I like, that I wanted to show you. And this shows that the total energy is this brown line right here, which I can highlight maybe yellow, and it's negative, right, for a bound system. Potential energy is the blue line, of course, that's negative. Kinetic energy is positive. It is the green line up above. And you can see that when you add the two together, well, first of all, the magnitude of potential energy is greater,
right? So we are going to end up with a total negative amount, right? Remember we solved earlier that that K, right, is equal to negative 1/2 UG, right? And you can see where I'm writing that there. So we end up getting 1/2 UG, but UG itself is negative. So if K is negative 1/2 UG, there's the bell, and this is a negative number, then obviously K is going to be positive, right? And so that's what this graph shows. Yeah, so pretty interesting, pretty neat. I think it says here that energy must be added to move a satellite from an orbit with radius R1 to R2. So by adding energy in, we are able to increase the potential energy, but the potential energy goes from, say, this point right here to a smaller negative number, which we consider to be a larger potential energy. Here is an example of a satellite increasing its orbit. This is kind of cool because right here, it is in a circular orbit right here, and with radius 1, R1. We hit the thrusters right here, and what that does, it extends it into an elliptical orbit right here. Now you might say, why not just have a force directed away from the planet, right? To have this rocket move into a larger orbit. And the reason you don't do that, right, is you don't do, say, this force right here, is because this spaceship has a lot of inertia, right? And so that's not going to work out really well there. So I'm trying to think what else. Also, force times distance, right? To accomplish work, we would have the distance pointing, we have the distance pointed this way, and the force pointed this way. That would be 90 degrees. So you'd be doing zero work if you pushed a force towards the planet and had the distance of the rocket moving this way. So that wouldn't work. So anyways, so what you do then, right, is you hit the thruster here to extend it into this elliptical orbit from this circular orbit, and then you hit it again here, and it puts you in a new circular orbit. And so I thought this was really cool, showing this, how to move into a larger orbit for a satellite. Let me go ahead and, I guess I didn't have to erase that. I think that's all I got. So anyways, have a great day. Hopefully you liked the lecture.